So today we're going to talk about the architecture of platforms for the SD-WAN solution, like the vEdge and the XC SD-WAN platform architectures. And this is your learning in the Cisco Live viewers, where for the SD-WAN, from the basic session, from the security features, from the hands-on labs, so you can just go through all the sessions. It's been updated. And today we are in this architecture part on the Thursday last. So the agenda would be for the today's session is introduction to the SD-WAN platforms. What are the platforms available for the SD-WAN solution at the moment with the vEdge and the XC SD-WAN, and the vEdge and the XC SD-WAN platform architecture, life of a packet on those platforms, and the software architecture of vEdge and the XC SD-WAN. So here when I keep saying that XC SD-WAN, which is nothing but the SD-WAN software integrated into iOS XC for Cisco routers. So the term we use here is the XC SD-WAN. And then the migration from classic iOS XC to the XC SD-WAN. So if you already have a Cisco router, how do we get to the SD-WAN solution with just with an upgrade? And the platform serviceabilities. And what we will not be covering today is how SD-WAN itself will work, what are the platform number, scale, performance, as it depends on various factors, and again the licensing part, also the virtual and the cloud platforms. There is this WebEx Teams, as you all know. You can join the discussion and put in your queries after the session. If there are anything in between, you can raise your hands. We can get to that. Then introduction to the SD-WAN platforms. So before we get into the actual session, let me just give you a brief on the SD-WAN architecture as a whole. So this architecture has three elements, basically the data plane, management plane, and the control plane. So to begin with the data plane, these are all our physical routers, or it can be of physical or the virtual again. And it supports the ZTPs, leverages all the routing protocols, and it can be placed on cloud as well, cloud platforms as well. And this data plane, these routers initiate the communication with the control plane. So the next is the control plane, the truly defined, software-defined networking architecture, like the brain of SD-WAN solution, central management of routing, policies, and the securities here. And here the control connections, the control plane and the data plane communicates, the data plane routers communicates to the control plane vSmart here. And then the management plane, this is a single pane of glass for a complete SD-WAN fabric. So basically you can monitor, you can troubleshoot, you can upgrade your devices, you can check real-time logs in it. So everything at all from your vManage dashboard. So we will also be having few of the vManage dashboard screens where we frequently visit and frequently play around stuff. I can show you the screenshots in the later part of the slide. It also supports RBAC and flavors of API, like role-based access control from the vManage. So you can set your privilege for any users accessing the vManage. And then there is this vAnalytics. So vAnalytics uses the machine language and artificial intelligence for carrier performance and predicting the bandwidth usage. And for the today's session, we will be talking about the data plane, the SD-WAN routers, what are the routers available, how are the architecture part, how the packet flow is in it, and a little bit of features in it. So as a whole, in the SD-WAN portfolio, the routing portfolio, we have this, as I said, virtual and the cloud platforms are also available. From the Viptala side, the vEdge cloud can be placed on the hybrid cloud or the public cloud again. And then there is this CSR 1000V. These virtual or the cloud platforms, the base functions are similar to the routers. So however, in this session, we will not be talking about that. And we'll be concentrating on the vEdge and the XC SD-WAN. So from the vEdge part, it's vEdge 100, 1000, 2000, and 5000. So these 5000 can be placed on the hub side based on the router capability. And the vEdge 100, 1000, 2000 can be go to the branch side. And from the Cisco side, XC SD-WAN, ENCS, Enterprise Network Compute System, ISR 1000, ISR 4K, and the ASRs. As you may know, ASRs can go to the headquarters DC or the hub side, wherein the other ISR and the ENCS can go for the branch side based on the requirements. So to begin with the platform overview, on the vEdge side, we have these 4 platforms, wherein the vEdge 100 to pick out has 5 inbuilt Ethernet ports, but then the 1000 has 8 1 gig SFP ports, and it varies in the 2000. The 5000 are all 4 NIM modularity ports. Like basically, when I say NIM here, it is not the same as we use in the ISR 4Ks. And this table is for your reference. Then this table gives you the CPU and the memory infos. Like the CPU for the vEdge 100, 1000, 2000 goes in the KVM Octane processor. Then the 5000 alone, a little bit of different. The Intel Haswell CPU. Then the memory. So as you can see, bigger the platform, higher the memory. And then for the Cisco, it's like XE SD-WAN to begin with the ASR 1000 series. So this ASR aggregation services router, as you may know, as I said, it can be placed on the hub side or DC or the headquarters. They are compact, powerful, rich networking services with the throughput ranging from 2.5 gig to 200 gig today. So the ASRs also has different, yeah.
Do you support dual RP like 06 or 09?
Dual RPs. Yeah, on the 1006 and the 9. As a platform, we should be, but in the XE SD-WAN integration, just the fixed chassis is supported. So yeah, as I said, the different flavors of ASRs, 1 RU, 2 RUs, until 13 RUs, wherein the 6, 9, and 13 goes to the modular chassis. And at this point in the XE SD-WAN, just the fixed chassis are integrated. The support for the SD-WAN is only on the fixed chassis. To be precise, ASR 1001X, 1002X, 1001HX, 1002HX. And this, the key differentiator on this ASR 1 case, instant service delivery capabilities, because the way QFP is designed, like the Cisco Quantum Flow processor, wherein we can directly code from layer 4 to layer 7, and which gives you less complexity and software overhead, where you can just enable any of the services from the CLI. And this table again for your reference on the chassis overview for the ASRs, the throughput, memory, CPUs, storage space, and the interfaces, SPA slots or EPA slots there. Again, however, the SPA shared port adapter or Ethernet port adapter is not supported yet. Only the fixed ports are being integrated for the SD-WAN solution. The 4K series. So as you all may know, the industry-leading branch router, we say this is. And this 4000 series comes with 4200, 4300, and 4400. Again, the 4300 and 4400 has different flavors. This 4200 can be placed for the small branch offices with need for modularity and WAN diversities. The 4300 can be placed for the medium branch offices with voice and compute capabilities, wherein the 4400 as a platform, as the higher the platform, you can place it for the larger branch with voice and capabilities, compute capabilities. There is a right corner, there are the features available for each and every particular platform. And all of these ISR 4Ks comes with security features integrated again with the SD-WAN. Just for your information, on 4200 and 4300 came into the SD-WAN integration last year, July itself, wherein the 4400s came in this year. The last one was the 4461, came into the support March 2019. The ISR 1K, again, has different flavors, and you can see the feature support on the right corner for this particular platforms. This ISR series router is SD-WAN ready with routing, switching, and wireless capabilities, like basically an all-in-one platform. This is the best WAN edge platform Cisco ever produced. That's what we get from the representatives. And the extension which you see, the 4P, 8P, are nothing but the LAN ports, like 4 LAN ports, 8 LAN ports, basically the switch ports. And then the ENCS, Enterprise Network Compute System, comes with 5100 series and the 5400. This ENCS is a hybrid platform that combines the best attributes of the traditional router and the traditional server. And it's recommendable for the SD branch. It's the best one for the SD branch. Here in this 5400 series has 4-core fixed CPU with fixed configurations. And then the 5400 comes with 6 to 12 cores with modularity. It also has switch modules in it, embedded switch ports. I'm just giving you the information and the changes overviews on this. And then this is the platform support matrix for the SD-WAN. What are the platforms available? What are the platforms we supported until March 2019? You can refer this, and you can also check the release notes for the platforms, the feature and the support informations. This is until 16.11 release. Next would be the architecture for the both vEdge and the XeSD-WAN. So to begin with, vEdge 100. As I said, vEdge 100 again comes with vEdge 100M or WM flavor, which is nothing but supports the 4G and the wireless. And also has 5 inbuilt Ethernet ports, as I said a little earlier. And the system is rated as 100 MB AES 256 throughput. It also has inbuilt GPS module and the USBs, the reset button, or just for your information on that. Sure, yeah.
When you order the cellular option, you have to choose the carrier before you order it?
The carrier, you mean the 100M or 100WM you're talking about?
Yeah, on like a 4G.
Okay.
When you order it, you have to tell them up front who you're using.
I'm not very sure about the ordering part.
The carrier you do, you have to order a Verizon one or an AT&T one.
Okay, so you have to have that in the SKU when you're placing the order.
Yeah.
Okay.
Thanks
There's
for
no
that.
eSIM or anything you have to balance between any of them.
Okay. So you're not going to-
Oh, thanks. And then the architecture part for the vEdge 100. The vEdge platform has a SoC design, like system on a chip design, and built on a KVM Octane processor. So let me just give you a brief on KVM Octane processor, a little bit of features in it. So this Octane is a family of multi-core processor, supports up to 32 MIPS core, with the speed ranging from 300 megahertz to 1.5 gigahertz. And this Octane hosts programmable packet processor, which are mainly intended to support IPv4 and IPv6 traffic, layer 2 to layer 4 parsing, exception checking, and several other DMA engines. So once the packet header has been stripped and stored, so we'll be talking about the life of a packet or the packet flow of the platform. So here, once the packet header has been stripped and stored, the payload can be forwarded through the system for the processing. The course in the Octane implements the integer MIPS 64 release 2 instruction set with several other Octane features in it, which in the final known as the CN MIPS 64. And the security is the hallmark of the KVM, wherein each MIPS core has its own cryptographic accelerators. The hardware accelerator algorithm include security hash algorithms, which are MD5, SHA, SHA-1, 2, 256, or 512, and AES. And the symmetric cryptographic algorithms, which are 3DES or DES, and asymmetric key operations, the RSA or Diffie-Hellman. Yeah, sorry.
Does this support NetFlow export?
I'm sorry?
Will this export NetFlow?
this vEdge platform supports NetFlow. You're asking me that. At this point, I'm not very sure about that. I don't want to assume and give you the answer. I'll get back to that.
So the vEdge, they don't call themselves NetFlow, they call themselves SafeFlow. So they do support the SafeFlow export.
SafeFlow it is.
Yes.
Thank you. Okay. So we have this dedicated DMA engines. So this architecture has this DMA engines. So for these dedicated DMA engines are the maximum I/O and system performance which are being placed for. And these engines, DMA engines, are provided for each of the hardware unit which accesses the memory. And there are these high-speed interconnects as well in the architecture. Basically, the hardware units and the cores connect through this high-speed interconnect. And this high-speed interconnect runs in same frequency as the cores. And there are these hardware acceleration units. Basically, multiple hardware acceleration units have been integrated into each of the Octane processor. The obvious reason is to reduce the software overhead of the complexities. And there is this acceleration units include, there are few of the components wherein like SSO unit, timer unit, FPA unit, PKI or PKO. So let me just give you a brief on those. SSO unit, which is nothing but the scheduling and synchronization ordering unit. So this unit manages the packet scheduling and ordering. And then there is this timer. This timer unit works in conjunction with the scheduling unit, and this is very effective for the TCP retransmission. And there is this FPA, free pool allocator unit, manages the free pools of data, which also include packet input data. And there is this PKI, packet input unit, PKO, packet output unit, as in goes by the name, manages the input packet and the output packets. And there are these security accelerators, the secure vault block, which you see on the block in the top corner, not in the corner, it's in the middle though. The secured vault block serves two major functions. It contains a true random number generator, and it also provides secure storage space for the encryption and decryption keys. And there are these application accelerators as well. These application accelerators differ in different cores, comes in different names. For example, HFA or DFAs, which is hyperfinite automata or dedicated finite automata, just an expansion of that. These HFA engines are in the Octane processor, which is based DPI engine with integrated memory, provides a very high performance, cost-effective, and effective solution for the DPIs. So it can be used for the QoS classification for any critical applications. And there is this authentic you see on the architecture, which is just a feature of a computer chip, which prevents the execution of any unauthorized software in the vEdge. And this Octane itself supports the standards. The base standards are the SerDes IO, PCIs, RGMIs, SGMIs, or 10 gig interfaces, the storage space SATA, and the USBs. The next is vEdge 1000. This vEdge 1000, the system is rated as 1 gig AES 256 throughput. As I said, with 8 1 gig SFP ports. There are these LEDs as well for the ports. And you have the USB options, the management gig interfaces. And also there is this console port, like console mini USBs. From the architecture part, it is very similar to its little brother vEdge 100 on the architecture side, just that little more powerful CPU with CN6130 CPU with 4 MIPS cores. As you see in the middle, the CPU where name is differs and the processor is different. That's it. And the memory is being increased to 8 gig to allow the higher scale. The vEdge 2000 comes with 4 inbuilt SFE ports, 1 gig SFE ports, and there are the 2 PIM slots. The PIM slot 0, if I say, so whenever it is installed with 8 into 1 gig SFPs, only 4 ports are available. Just for information, it's there in your table also for your reference. And there is no restriction as such for the PIM 1. The system is rated as 10 gig AES 256 throughput. From the architecture part of 2000, the vEdge has a very similar system on a chip architecture like its brothers in the family, vEdge 100 and 1000, which much more powerful CPU as CN6880 CPU with 32 MIPS cores. The memory is again scaled as per the platform for 8 gig. Then the 5000. The 5000 has these LED screens, management ports with 4 modularity, like 4 NIM ports. And there is this table for your reference on the SFP port support. On the architecture part, again the vEdge 5000 system is rated as 20 gig AES 256 throughput. And the architecture part, the vEdge is a different from its family, vEdge family, a different breed, which is again, it uses the Intel Haswell CPU. Again, system on a chip, but Intel Haswell CPU with 14 cores and 2 threads per core. So as you can see, there's the NIM module connected to the cores through the PCI bus. And there is this PCH platform controller hub, which connects the management interface USBs in the consoles. This is for your reference on, oh, sorry, yeah.
I just wanted to confirm for the whole vEdge series, in terms of flow, these are all C-flow in many devices, is that right? Or any differences there in terms of what they mean?
So,
Can you repeat any differences on what?
Yeah, so these are all producing this C-flow packet export, is that correct?
That's right.
Flow export, they're all the same.
That's correct.
thank you. And then for the XE SD-WAN, again the platform architecture. So we were having an overview on the vEdge. Now to begin with the XE SD-WAN on the ASR part, as you all may know, ASR has 3 basic building blocks like the control plane CPU, forwarding plane, and the I/O. This control plane manages only the system components in the processes, does not do any of the data plane activities. Again, the forwarding plane, which is the data plane, does the packet switching and the features. And here, the forwarding plane, this is where the QFP resides in, Cisco Quantum Flow Processor, multi-core processor. This QFP is a multi-core processor architecture, as I said, with 62 multi-thread cores with 4 threads per core. So together, looks like 248 different cores are available to process a packet. This QFP can be cascaded into 2 for better performance. And there is this I/O, which does not do any of the forwarding intelligence, just for the connectivity. And there is this control CPU, the control plane. The control CPU is the one responsible for communicating with the vSmart controller. The integration part comes in, wherein this hardware from the control plane communicates to the vSmart controller through a protocol called OMP. So to download the routes locally and put it into the resource DRAM. So we will be seeing the software architecture on that part, the later slide. So this, as you see in the forwarding plane, there is this TCAM in the left corner, which is the hardware acceleration of classification for all data path features, like ACL, NAT, QoS, etc. And there is this resource DRAM I said. So the PPEs, the packet processor engine, will quickly do the hardware lookup on this resource DRAM and make the forwarding decision. Why? Because this resource DRAM has a condensed version of FIP table in it. And then the packet, the features will be transferred to the packet buffer DRAM. So and it be scheduled for the, it's for the BQS, which is buffer queuing and scheduling. Basically, the traffic manager will schedule the packet out of the system. And then there is this crypto processor. So we keep saying that Cisco, we concentrate on the security solution, secured platform. So there is this crypto processor, dedicated crypto processor, to handle all the intense computation of cryptography, which provides the higher bandwidth for the IPsec capabilities. And there are these ECI links, like the interconnects, hooking up all the I/O ports to the aggregate traffic up and send the traffic back down. That's the ECI links. And this table is resource comparisons for the fixed chassis, the QFP resource memory, or the TCAMs, the control CPUs, the CPU all Intel quad-core CPU with different clock rates, and the memory, again, bigger the platform, higher the memory. 8 gig is the default for ASR 1001X, wherein in the 1002X, HX is 16 gig, where it can be expandable up to 32 gig. You can refer this table. And then the platform architecture for 4400, like ISR 4 case. This is the physical separation of control plane and the data plane. It's similar to the ASR 1 case. And there is this dedicated forwarding, crypto, the scheduling resources also. And the control plane runs on iOS XE and with 4 core, which is 1 core runs with the iOS D, used for the iOS SD, which is your iOS daemon runs in. 3 cores are the service plane, where you can install your service containers and any application on that. And this data plane is a microcore on 6 to 10 cores. And the architecture-wise, it is all very similar to the ASR 1 case. So the latest in the market, which is 4461. So there's one difference we just wanted to point out on the architecture part for the control plane and the data plane, which is the 4-core Intel Xeon architecture, just that x86 for the 4431 and 4451. So here the 4461 is the new one, which is Intel Xeon architecture, and the data plane comes with KVM SoC architecture. And there is this data plane fixed memory as well for the data plane, again in this 4461, which is 4 gig. And the base functions and the remaining operations are all similar to the ASRs. The next one is the 1100 series and the 43 and 4200. Here, this is the unified architecture for a single socket CPU, where both of the control plane and the data plane runs with the iOS XE. And this platform also has this dedicated forwarding, crypto, or the resources, scheduling resources. Also, the base functions, very similar to the ASR 1 case. Here, when I say the 4-core plane for the 1100 series, wherein it just separated for 2 cores for the control plane and 2 for the data plane. And however, the service plane, the service containers, the service plane it's not used in the 1100 series at this point. And then the next one, last one is the ENCS, Enterprise Network Compute System. So there is this VNFs requires SRIOV, which is single root IO virtualization driver for Intel 40FL, just for your reference I'm talking about. And there is this NIM support, and there is this data path and control path, the different color lines, the blue and the green. You can have a look on the slide. And there is this gig interfaces connecting to the uplink. There are these high-speed backplanes as well. There is this software switch, which can be 50% to 70% slower than the hardware offload. And for the architecture part, on the platform hardware architecture, that's it. And to continue on this for the life of a packet on both vEdge and the XE SD-WAN, Jason will be running the show.
All right, thanks, Vijayendra. Any questions before we move on? So just recap, there was a gentleman there were asking at the beginning if the ASR 1009X supporting modular redundant Route processor, the answer is yes, but the modular chassis does not support SD-WAN, okay? It's only the fixed chassis support SD-WAN. And this gentleman asked when he ordered the vEdge 100 with the wireless module, does he make sure order the right part? If connecting to the Verizon, you need to make sure you order the PID with the Verizon ones. If you're using AT&T, you make sure you need to order the proper LTE and 3G support with your providers. And this gentleman was asking about the C-Flow. Yes, C-Flow is supported across vEdge 100,000, 2,000, 5,000, and consistent on the vEdge.
And the ISR, ASR, let's get the NetFlow v9.
So the question is on the ISR, ASR going to be the NetFlow v9? Correct. Yes, sir.
You know, is there a roadmap of what's going to happen between the C-Edge and vEdge? Because we're doing a deployment with vEdge, but we have ISR 4Ks at all of our sites. We're going to start out that way, but in terms of like Cosmo versus NVAR and C-Flow versus NetFlow, has Cisco decided what that's going to look like over the next year or two, or is that still being worked out? Will there be true parity, or will those differences stay the same for a while?
So the question is the vEdge and the ASR, ISR product, they're going to converge in terms of implementations?
Yes.
Okay, so the answer is no. vEdge going to stay with Cosmos, C-Flows, and the ASR, ISR family going to stay with NVAR 2 NetFlow. Okay. There's no plan to have the same implementation. Anybody else? Okay, let's go a little bit deeper. We're going to give you a packet walk. So we're going to start with the vEdge platforms, then we will do a XE-SD-WAN platform. This is the block diagram Vijay just showed you. The vEdge 1000 has 4 MIPS core and the number of hardware acceleration processors. So as the packet coming in from the ingress interface, the packet input processor going to perform some early processing on that packet, including the exception check and the checksum. It's going to start from the layer 2. Check the layer 2 type, FCS, frame error, length mismatch, then moving up stack to IP header, IPv4, IPv6 header, checksums, malformed, TTL bit, IP option header, then move up to the TCP UDP header. Checksum, the length, the TCP flag, bad port. After that, it will perform ingress classification based on the diff surf values, based on the toss values on a per port basis. And that classification can be remapped using the QoS configuration we talk about in a moment. As a result, it will create up to 7 tuples hashtag. That is your ingress port, the toss value, protocol, then the source IP, port, destination IP, and port. And get packet to be ready to be processed by the MIPS core. Then the packet will be written into the packet buffer memory. That's the layer 2 cache and the DRAM. The FPA, the unit, and going to allocate a buffer and then link the buffer and align the packet data in the memories. The packet input processor is going to perform an add work operation to add a pointer to the input work queue that's maintained by the SSO unit. So that's the synchronization and the scheduling ordering unit, which maintain the workflow to the cores and also maintain the ingress packet order. And the scheduling is going to be based on your packet priorities, the ingress order, and the current, the flow logs. Then the core is going to ask for a piece of work to do. So the SSO is going to return a pointer to the packet data buffers. So the core is going to process that packet according to the feature invocation array we call the FIA, which we're going to talk about that in the software architecture section. So the core is going to read and write the packet data in the buffers and processing the feature, the SD-WAN features to completion. After processing the packet data, the core will send the packet data buffer pointer, the data offsite, and the appropriate packet to the appropriate packet output queues to the packet output unit. Then the core is free to processing the next packet. The packet output unit is responsible for packet transmission. Packets are queued on the egress interface with multiple prioritized queues. So SD-WAN support up to 8 queues on the egress interface. The packet output processor is going to send the packet from the internal memory over the bus to the egress port. Then after that, the packet memory will be freed up automatically. Any question on the vEdge flow? Make sense? Too easy? All right, let's take a look at the XE-SD-WAN platform. And this is the block diagram of ASR 1001X, very similar to the 2HX Vijay just talked about it. Has a single QFP ASIC, 31 PP processor, 4 thread per PPE, make it look like there's 124 processor to simultaneously processing the packet. BQS is a traffic manager in the hardware ASIC. It does all the schedulings and the queuing based on your QS configuration. And there's a IPsec chip, does all the IPsec encryption and decryption in the hardware. So we're going to first talking about the example packet coming from the WAN interface toward the LAN interface. So in the SD-WAN, we use the terminology of a transport VPN and a service VPN. So transport VPN is your overlay VPN coming from the WAN. Service VPN is the VPN or the VRF, if you will, connecting to your LAN port. So sometimes we see traffic coming from WAN to the LAN. Sometimes we see from transport VPN to service VPN. Is all the same thing. So packet coming in from the ingress port, from the LAN port, and this is going to be IPsec packet. And the packet can be written into the packet buffer memory. The dispatcher is going to allocate one of the PP thread to process that packet. Then the PP thread will process the packet according to the FIA. During that process, the PP is going to recognize, okay, I need to do a decryption before I send the packet to the LAN interface. So it's going to write the packet into specific recycle queues in the BQS, in the traffic manager. Then the packet dequeued from the BQS and passed on to the crypto engine. The crypto engine is going to decrypt the packet, return the packet back to the dispatcher. And dispatcher find available PP thread. Doesn't have to be the same thread, just processing that packet, can be any thread available. Then run the remaining SD-WAN feature to completion. Then PP send the packet to the BQS, and the traffic manager going to schedule the packet out of the LAN interface according to your QS configuration. Yes, sir.
So at what point are you building the flow table?
So the question is, what time you're going to build a flow table? I am going to show you that in the software architecture when we're talking about the FIA.
Great, thanks.
Yeah. And we're going to take a look at another example of the ISR 4331. And this time, we're talking about a packet coming from the LAN interface going out to the WAN interface. And this is the forwarding architecture of ISR 4331. It has 4 data plan cores. The front panel gig interface is directly connecting to the data plan. This is your typical WAN interface. And through the multi-gig fabric, connecting to the NIM port. The NIM module is the one you're connecting to your LAN port. Okay. I don't have an animation for this, so just follow my word, okay? So packet coming in from the LAN interface through the multi-gig fabric, the packet will be written into the global packet memory in the DRAM of that data plan. Then there's a distributor going to assign the packet to one of the PPE thread, and that PPE thread going to executing the SD-WAN feed. And during that process, the PPE is going to recognize, okay, I'm going to send the packet to the transport VPN. I need to encrypt the packet in IPsec. Then the packet gets copied out of the GPM and sent to the packet buffer memory. So that DRAM is partitioned between the GPM and the packet buffer memory. And one of the threads in that I/O crypto core is the traffic manager thread. It's equivalent of the BQS you see from the ASR 1000 architecture. And that BQS thread is going to pick up the packet and send to the crypto thread. Then the crypto thread is going to do the decryption and send the packet back to the distributor, and the distributor find another PP thread available and run the remaining feature to completion and send the packet to the WAN interface, which is the front panel gigi port. Yes, sir.
So when you decide to move 4331 from an underlaid factory router to SD-WAN, does that require certain hardware upgrade besides the SD-WAN licensing part?
So the question is, when you move the ISR 4K from underlay to the SD-WAN overlay, do you require any hardware upgrade? The answer is no. The only thing you need to modify or upgrade is to load the XeSD-WAN software, which we have a section vision. It's going to talk about how to do migration from classic iOS XE to XeSD-WAN software.
But not even DRAM? You don't need the extra DRAM to account for the SD-WAN?
So the question, do you need actual DRAM? The answer is no. You don't need actual DRAM.
Thank you.
Yes?
Is the interfaces important? You mentioned the front panel interfaces versus NIM interfaces. Is that critical? Or?
So the question is, does the interface matter? Critical, the NIM versus the front panel interface? Yes, the NIM is always used for the LAN connection. The front gig is not always used for the WAN interface connection.
The 3 gig interfaces on the front panel on 4331. Can I use one for the WAN and one for the LAN?
Oh, I see what you mean. Yes, absolutely. The question is, can I use the front panel gig interface for both WAN and the LAN? Yes, you can do that. We're good? Okay, let's talk about the software architecture. First, we're going to talk about the vEdge, then we talk about the XeSD-WAN. What you're looking at here is the vPlus software stack. When you power up a vEdge router, the Linux running process is going to start and initialize other process. The first one is called the system manager. System manager is the process to build up the vEdge software architecture, what you're looking at here right now. So the system manager going to look at the configuration file, the system configuration file, and look at, am I vEdge, or am I vSmart, or am I vBung, who am I, and what other process I need initialized. So you're going to start to building up the systems. You're going to spawn, monitor, and terminate all other process. It's also going to responsible for collecting vital system information, like a CPU memory status. Another process is called the chassis manager. Chassis manager is responsible for interface initialization. And there's also config manager. Config manager is the process to communicating with the vManage, to download the configuration from the vManage and host the configuration locally on the router. And vDaemon. vDaemon is the process responsible for start the system orchestration. So vDaemon is going to set up the control tunnel to vBound, vSmart, vManage in TLS or DTLS tunnel. So it's going to acting as the tunnel endpoint and does all the encryption and decryption of those tunnels. All the control traffic, like OMP, Overlay Management Protocol, netconf message, all go inside those control tunnels. The OMP, Overlay Management Protocol, is used to communicating with vSmart to learn all the route, the overlay route from the vSmart, and also advertising the local route up to the controller. RTM, Route Table Manager, think of that as a RIB in iOS, Route Information Base. And you have the TTM, Tunnel Table Manager, responsible to building up the tunnels. So once you configure a T-log, so in the SD-WAN world, they use the terminology of a T-log. You can just think about it is a tunnel, okay? And so once you configure a T-log, the OMP is going to know the config and then notify the TTM to create the tunnel, and TTM also going to maintain that tunnel. And you have the FTM, the Forwarding Table Manager. That's equivalent of a FIB in iOS, if you will. And last, you have the Forwarding Policy Manager. Forwarding Policy Manager is going to maintain all the forwarding policy, like the application route policy, data policy, so on and so forth. So this is the whole system of the Viptela software. Any questions? Yes.
Is there somebody actively working on the documentation to get it in line with what we would typically be accustomed to with Cisco? Because there's not a lot of documentation.
Is there anyone working on documentation of what content?
On the Viptela stuff?
There are, if you just Google Viptela configuration guide, you see the whole list of a configuration guide. And Viptela, if you just search on Cisco SD-WAN release note, their release note to publish every release what new features there and any command line changes. And
Well, I guess I'm looking at, like OMP, for instance. Is there good documentation how OMP works out there that's publicly shared, or? Okay.
yeah, so the question is there any documentation to show how the OMP works? And this gentleman answered yes.
Okay.
So
Okay. Yeah.
yes.
Which process runs OSPF or BGP?
So the question is which process run OSPF or BGP? The OSPF and the BGP is going to be run as part of the RTM, the Routing Table Manager process up there. Okay, how many of you are familiar with the iOS XE architecture? Okay, so before we talk about the integration, let's first take a look at the iOS XE architecture. iOS XE is a modular and distributed Linux operating systems. You have the Linux kernel. On top of that, there are 3 subsystems. There are RP subsystems running the control plane, manage the system, FP subsystems running the forwarding, the data plan, and the I/O subsystems running the interface. And on the RP subsystems, you have the CMAN RP, we call it chassis manager on RP, that's responsible to bring up the systems and initialize other process, and also monitor the system status, temperature, voltage information. iOS, running the control plan OSPF BGP, and also responsible to generate the configuration, build the RIB, compute the FIB. Then the FIB will be downloaded into the FMAN RP, forwarding manager on the route processor, which maintain a copy of the FIB and push the FIB down to the FMAN FP. That's the forwarding manager process on the FP subsystems. So FMAN FP is going to maintain a copy of the FIB and use that provide interface to the QFP client and driver. And the QFP client driver use that information to program the QFP ASIC and the QFP resource memories. Then you have the QFP microcode, which is run the actual QFP microcode to executing that feature, the data path features, and all the packet processing. On the ISR 4K, ISR 1K product, you have the DPDK, which provide a library to work with the underneath x86 processors. The I/O subsystems, you have the CMAN CC, we call it chassis manager carrier card, which is maintain the interface driver and the forwarding path FPG on the interface. Then you have the NGIO process, which maintain the interface driver and FPG on the ISR 4000 and ISR 1000 family. So this is the classic iOS XE operating systems. And when you upgrade to the SD-WAN software, the architecture is going to look like this. So we're going to run the Viptela software stack side by side with the iOS on the RP subsystems. So this is what we call the sidecar approach. Does anybody watching a sidecar race? So this is an interesting game and an interesting race. You have the pilot, they don't call it driver, they call it pilot. He's in the kneeling position in front of the engine and with hand near the front wheel to control the speed and the direction of the vehicle. And you have the co-pilot, which moving around the platforms to balance the vehicle and gain tractions when coming to turns and also help the pilot when come to drifting. He's also typically the first one to find out if there's engine problems because he's right next to the engine. So this is the same idea we're taking, same approach we're taking when we decide to do the Viptela integration. And the iOS XE is going to be the pilot, and the Viptela software stack is going to be the co-pilot. So to make this a winning team, we need to do a couple of things on the iOS. So two primary functionality we're adding in the iOS is called OMP agent and the SD-WAN subsystems. OMP agent. Think about you have the OMP process communicating with vSmart for your overlay route. And you have the OSPF BDP from iOS to run your LAN side of the routing protocols. So you need a process to be able to distribute from the service VPN to the transport VPN and the other way around. So OMP agent serves that purpose. And another process called SD-WAN subsystems. So iOS is the process, is the host of, you have all the interface configuration. The interface comes up. They're going to register the interface in the iOS. And you also have the iOS to configure all the VRFs, so on and so forth. And the SD-WAN subsystem is the process going to synchronize those information from the iOS to the SD-WAN. And also the iOS also needs some information from the SD-WAN. And so the SD-WAN subsystem is going to establish bidirectional communication to synchronize the required state between the iOS and between the service VPN and the transport VPN. So this is the XE SD-WAN software architecture. Yes, sir.
This is probably a good time to revisit my question about the flow then, right? So,
Right there, next slide.
okay, next slide.
Coming.
Over there. All
The
right.
fee is coming. So we said when the processor, either a vEdge or QFP or x86, when they're processing the packet, they're going to follow this fee. They're going to run this SD-WAN fee to feature completion. So we're first going to talk about from the LAN to the WAN direction. Then we will talk about the from the WAN to the LAN direction. The first feature going to be executed from the LAN to the WAN direction is called SD-WAN interface ECL. This is not your classic iOS ECL. This is the Viptela style SD-WAN interface ECL. It allows you to match on certain parameters, like the toss value, prefix, protocol, and then you can take actions. You can either permit the traffic into the system or drop it, or you can police the traffic. There are a number of actions you can take on. It will do a self-lookup and figure out, okay, this packet should be sent toward the WAN interface. Then it will going to do a deep packet inspection. So this is where, to answer your question, as part of that N-bar, it's also going to perform the flexible NetFlow functionality. So this is where, if this is a vEdge, you're going to run the CFlow. So this is where that feature happened.
And this is coming off the service VPN.
Pardon me?
This is coming off the service VPN.
That's correct. So the question, if this process is running on the service VPN, yes. We're talking about the packet coming in from the LAN interface. That's the service VPN. Then it's going to executing that application route policy. So the application route policy is that in a vSmart, you're able to define service level agreements for the applications. Let's say this is a voice application, and you see I need a latency less than 150 milliseconds, and the packet drop less than, let's see, 0.1%. So the application route policy is going to apply it from the vManage to the routers on the data path, and they're going to match on the incoming packet, because at this point it has done that deep packet inspection and know what application it is, going to match this application to the appropriate tunnels, so that to meet your service level agreement for the application. Then it's going to executing that data policy. That data policy can be a global policy, we call centralized policy, to define your network segmentation, the VPN memberships, or can be a localized policy, which is commonly is the QoS policy. Then it will do a lookup process, walk through the OCE, output chain element, to get packet ready to be processed on the tunnel interface. On the tunnels, it's going to add the VPN label. So in the SD-WAN, they use the VPN label to identify the VPN or VRF membership, and then add a tunnel encapsulation. So the SD-WAN use a GRE over IPsec type of encapsulation. So it has a 20 bytes GRE header, followed by 8 byte of UDP header, 36 byte of ESP, encrypted security payload, 4 byte of VPN, then the payload. Then get pre-routed the packet to the WAN interface. On the WAN interface, the IPsec encryption going to be added in the transport mode, which means the IP header is not encrypted, but the payload are encrypted. Then add a layer 2 encap and transmit the packet out of the WAN interface. And that TX is where your egress QoS policy will be executed, and we have a queuing policy we'll talk about in a moment. and the packet coming back from the WAN interface to the LAN, you're going to have the first feature to be executed called the SD-WAN filter. So the way the SD-WAN works is that the packet coming from the WAN interface, they all IPsec encrypted. All TLS, DTLS encrypted. So only the encrypted traffic are allowed coming into the system by this filter. And from the known sources, because the router knows who are my TLOG, who are my tunnel peers. So only the router are part of the SD-WAN fabric and encrypted are allowed from the WAN coming into the system from the WAN interface. Then it's going to executing on that SD-WAN interface ACL, do a self lookup, and then figure out this packet should be sent to the LAN interface, or if it is a for us packet, which means I'm receiving a control plane message from the WAN interface, I'm going to pound this packet to the control processor. Decrypt IPsec packet, process the packet on the tunnel. On the tunnel, it does a VPN lookup to figure out the VPN membership, then pop the label, do a self lookup in that VRF to find out my next hop and adjacencies, then apply application route policy, the data policy, we talk about it. Then on the LAN interface, add a layer 2 incap, and executing the queuing policy on the TX. So this the fear. This is how the SD-WAN feature get executed on the router. So next, yes, sir.
So let me just cut to the chase here. Transport VPN. Where you pull the data for the construction of the flow table, do we have access to the transport VPN ID? Are we going to know which transport VPN these conversations are coming out?
So the question is, do you have the information of the transport VPN ID of those flows? Yes, absolutely. If you look at the vManage, I don't know if Virginia has one of the UI. Yeah, in the vManage UI, you're going to know the flows and which transport VPN they're coming from.
Do I have to get that from vManage, or is that exported as part of your flow record here in FOB?
You need to get that from vManage.
Okay, so vManage is stitching that together.
That's correct.
Got it. Okay.
So as the packet transmits from the ingress to the egress direction, there are a number of touch point, the QoS will be executed. So first, there is a port or VLAN-based policing. This is a vEdge specific functionality not supported in the XE-SD-WAN. Then after the packet inspection, the classification, you can apply an ingress ACL, access control list, to match on 5 tuples, which means match on the flows, and you can apply action of a policing, or you can apply the action of a rewrite inner DSCP values. So do a remarking. Then there's a data policy. On the data policy, you're not only able to match on the flows, but also match on the applications. Then you can do policing action and classify the traffic into different queues and rewrite the inner DSCP values. So you can do a hell lot of more actions using the data policy. On the egress direction, you can also apply egress ACL, which match on the flows, rewrite the inner DSCP bit. Then the port VLAN-based policing on the egress interface. And there's the DSCP rewrite rules, and this is the moment allow you to rewrite the outer encapsulated GRE header DSCP values. Then apply the shaping on the egress port, and the traffic will subject to your queuing configuration. Policing. SD-WAN implement a very simple single-rate policer. The confirmed traffic will be forwarded. The exceeded traffic will be dropped. the policing is supported on the ingress and egress direction. We said the ingress and the interface and the VLAN-based policing is only a vEdge specific feature, not supporting the XE-SD-WAN. The access list and the data plan policy policing are supported in both vEdge and XE-SD-WAN. The ACL, you can match on the flows and apply the policing in both ingress and egress direction. The data plan policy, you can match on both flows as well as the applications to apply the policing only on the ingress interface. Marking, remarking. So you can either match on flows or match on applications and rewrite the inner and outer DSCP values. When you rewrite the inner DSCP values, the inner DSCP value automatically copy to the outer IP GRE encapsulation headers. And in the egress interface, you can apply the DSCP rewrite rule that only apply to the outer DSCP values. Shaping. The shaping is only supported on the egress interface. Conformed traffic are forwarded. The exceeding traffic will be queued. The queuing is using the weighted round robin, WR. At this moment, the egress, the shaping is only supported on the interface level. Queuing. So the queue can be classified using flows or applications. On the egress interface, you can have up to 8 queues. The Q0 is what we call the low latency queue, or you can call the priority queue, if you will. The low latency queue implementation on the vEdge is using the strict priority policer. Does anybody know what that means? What is strict priority policer? It means that during congestion, the traffic is still going to be forwarded, not subject to the congestion. The conditional policer, that's the implementation of the priority Q0 on the XE-SD-WAN platforms, which means during the congestion, the traffic in the P0 are subject to the congestion, to the policer drop. The control traffic, we said, including the DTLS, TLS traffic, BFD packet. BFD packets are used to monitor the state, the liveness of the tunnels, always go inside the Q0. So on the vEdge, because they use strict priority policer implementation, so not subject to the low latency queue policer drop during the congestion. And the XE-SD-WAN platforms, they encrypt the traffic, the control traffic, TLS, DTLS, subject to the conditional policer drop, but the BFD packet not subject to drop, which means the BFD packet always gets transmitted, even there's congestion occurred. And the Q1 to Q0 are scheduled using weighted round robin. Each queue, you can apply either tail drop or you can apply a random early discard. The right drop profile on the vEdge are linear, which means you have X percentage of the queue depth, you're going to have X percentage of the drop probability. On the iOS XE, we're using the classic WRED implementation on the per precedence basis. Those 2 slides is for your information only. I mean, I'm a CLI geek, and I like to know what actual CLI applied on my box. But for most of you, you don't need to know, because you're going to use the vManage. You're going to follow the workflow, click, click, click. That's the whole point of SD-WAN deployment. It's the simplicity. So vEdge is going to hide all the complexity and the different platform implementations, and so you don't have to worry about what's happened underneath. IPsec data plan. So all the traffic in the SD-WAN fabric are IPsec encrypted. And there are 3 elements to ensure that IPsec connections are secure. The first one is authentication, to authenticate the origin of the data. For that, we're using the 2048-bit of RSA. The encryption itself is using AES 256-bit cipher, and the ESP HMAC SHA-1 and the anti-replay going to ensure the integrity of that data. Encryption. So the data plan encryption and the key generation is using 256-bit GCM. The same key is used for the encryption of the outgoing traffic by the router, also used by the peers to decrypt the traffic. And each router will periodically generate the AES keys and update the keys using the OMP route packet to the vSmart. And the key is generated on the per TLOC basis, so per tunnel basis. And the vSmart is going to advertise this key, the OMP route packet, to all the vEdge or the XESD-WAN routers, which are part of the fabric. So this is a very simple and scalable way of doing the key exchange. And the liveness of that security association is monitored and tracked by the BFD packet. Data plan integrity. So the ESP, encrypted security payload, going to protect the inner header and the data payload. The authentication header going to be used to protect the entire data packet, including both inner and outer headers and the payload. And the anti-replay is going to make sure there's a unique sequence number generated for each packet, and the receiving packet is going to make sure it only receives the packet with the unique sequence numbers. And the VPN label is used as to identify that VPN membership of the packet. Application classification engine, also we call the DPI, Deep Packet Inspection. So on the vEdge, some of you already know, the implementation is using the Cosmos, a third-party DPI engine, which run number of DPI methods to able to perform the application classification. For example, DNS caching, pattern matching, the port-based classification, protocol data signature, session behavior, correlation of the sessions from different flows to identify that application. On the XESD-WAN routers, we're using the Cisco homegrown NBAR2 network-based recognition engine with the combination of some optimization techniques, including the snooping of the DNS packet, machine learnings, we're watching the socket and do the service discovery, and also have ability to support custom applications with the ability to do the DNS as a services. And we didn't stop there. And we continue to innovate, and we bring the deep packet inspection to a network-level services. We call the SDAVC, Software-Defined Application Visibility Control. So what you're looking at here is the SDAVC architecture. You have some routers in the network is acting as a sensor. So they're the one doing the deep packet inspection, and they're able to send their sensor data in a JSON UDP format up to the controller. The controller is a container running on the vManage. So the controller is going to aggregate and synchronize the application state across the network. to identify the application, to do precise application classification. It can solve the problem like asymmetric routing, which is a pinpoint for any DPI engine as a standalone device. Because for DPI to identify the application properly, it needs to see the bidirectional transaction of that applications. But in the SD-WAN deployment, it's common that you have the outgoing traffic as it's going out your MPLS circuit, but the incoming traffic can coming back from internet circuit hit the other SD-WAN routers for that site. So you have this asymmetric traffic flow behaviors. With the SD-WAN AVC, controller is able to aggregate, see the entire network from the sensors in your SD-WAN fabric. So you're able to properly solve the asymmetric routing issues. It also has the ability to do first packet classification. That's very important for the direct cloud access use case. You want to redirect your Microsoft 365 traffic to Microsoft Azure. That decision has to be made on the very first packet. And that's what can be supported with the SD AVC. It can also, the controller can also serve as external gateway connecting to other trusted sources, like O365 Cloud, the DNS services, the Cisco Unified Call Manager, Microsoft Link, OpenDNS Cloud, to connecting all other cloud services which has the trusted information between the DNS name, the domain name, the IP address, the port, and the actual applications. So it's able to pull those information and synchronize them together to build what we call the application rules. So it can push the application rules in a simple format, application ID, the IP, and the port, back to the SD-WAN fabric, to the network node, which are acting as a consumer. So the consumer can simply match on those application rules to perform the application classifications without doing the deep packet inspection and executing that application route policy. So this is the SD-AVC architecture. Also, the controller has the ability to update the NBAR2 protocol pack to thousands of devices in the network. Yes, sir.
If we deploy the vEdge and we have asymmetric paths, will there be a way to stitch that together, or would we only be able to do that with the NBAR SD-AVC?
So the question is, when you deploy vEdge, is there any way to stitching the asymmetric traffic flow together, or have to use the SD-AVC? The answer is you need to use the SD-AVC to solve that asymmetric routing issue.
So is there a way to use that with the vEdge, or is that only with the cEdge?
So the question is, is there a way to use that with vEdge, or you have to use the cEdge? You need, the SD-AVC is only supported with the cEdge, the ASR, ISR product. We call it XE-SD-WAN product. Okay, any other questions before I hand off to my friend to talk about the migration? Yes, sir.
I had one about the TOS. You said the control plane traffic was on Q0, but then on the slide it says that the DTLS, TLS tunnel traffic was not subject to drop. So I was confused about that. What did you do?
So your question is, I said the control traffic could go to Q0, and you're concerned about the TLS, DTLS traffic and not subject to the QoS drop?
Yeah, it says subjected to policy drop. I didn't understand that.
Yeah, so they're twofold, right? So the control traffic, we said like OMP or netconf message, those are part of the control message. They all go into the TLS, DTLS tunnels, right? The implementation for the vEdge and XE-SD-WAN are different. So on the vEdge, the implementation is any traffic in the Q0 not subject to the policer drop. And on the XE-SD-WAN, the BFD not subject to the policer drop, but the other TLS, DTLS traffic which including your OMP update, your netconf message, are subject to QoS drop during congestion.
Only for XE.
That's correct. All right.
Thanks, Jason. So the migration part. So if you already have a Cisco router, XE router, you can just migrate it to the XE SD-WAN with just an upgrade. There is this upgrade we cannot talk about is from the vManage. It's like a bootstrap configuration from vManage. So to give you an overview on this, we will be creating a template, like a feature template, and then downloading a config file and put it into the router and boot the device with XE SD-WAN. So it is as simple as that. So to begin with, the prerequisites for this is 18.4.0 for the vManage, the controllers version, and XE SD-WAN is 16.10.1 or higher. So this comes in handy. It's useful when the ISP did not give you the DHCP address. There is another method. If there is the DHCP, you can just go through with the PNP process itself. So here, the first step is to download your serial number from the portal and then upgrade it to the controllers, update it, and then you have to send it to the controllers, like make it to the valid state. That's it. So here I've just taken the 4400 as an example and loaded it to the controllers. And then, as I said, you'll have to create a template. Like basically, from the vManage, anything we do to the router, it will be as a device template, CLI template, or the feature templates. So I'm just creating a template for the device which has been attached. And that template, so the configs which you're going to put in here. So once the router boots up, so the ones which we're creating, all of the informations like system IPs, the vBond IPs, the interfaces, all this informations will be giving into that template. So this information will go into your router once the device comes up with the XE SD-WAN image. So you'll just have to fill in those details and update it. Then here, so we are just pushing this template to the device. It is just showing as done scheduled because the device is still offline. So once the device boots up, it will recognize the configs which you are putting in the previous slide, and then it will just come up automatically and join the fabric. So here the background process we can be looking at, like what is happening. The device is offline, updating the device configuration, the vManage, and all the stuff, the background information basically. And then the next step is to generate the bootstrap config. So what is it? Like if you see there, it has been scheduled sync pending, and then there is this, in the corner, we see 3 dots wherein there are a few other options with the generate bootstrap config. You just have to click on that, and the configs will be generated. There is a default configuration with the bootstrap, and it will be generated with the configs which have been added in the previous slide, the template side. And then you'll just have to select the cloud init. The next step is you'll see the preview on it where you can download the config. So this download, you can download it anywhere. Just make sure that you save as the CFG file, .cfg file. I've just taken a Cisco SD-WAN.cfg because this is very important, because once the router boots up, the device, the processor will look for this .cfg file in the boot flash and then bring up the router. And this step, it's our traditional way of getting the config file to the boot flash. It can be TFTP or the USB. Just taken the USB method here. And the basic checks like config registration value, config register value 2102, and the XE SD-WAN image would be as the UCM K9 image which you see here. So you just have to make sure that the router boots up with this image. You can set the boot statement for that in the device. And you can also delete the original image, the XE image, and then put it in somewhere else instead of the boot flash, so the router boots up with the image which is available in the boot flash. Just in case, if you just want to go back to the XE image, if after booting up with the XE SD-WAN, you will have to break the router to the ROM on mode and boot it. And yeah. Then once the router boots up with the XE SD-WAN image, it will look for the .cfg file, and then the router will come up. It will abort the PNP process, and then you'll just have to wait for a few minutes wherein it will just join the SD-WAN fabric, the vManage. So once it's joined, from the vManage dashboard, you can see as in sync. You can also verify it on the device with the control connections. So control connections. So for the XE SD-WAN, it will be as show SD-WAN control connections. You can also, the BFD sessions would come up. And just for your information, if it's an on-premise implementation, just make sure that you install the root certificates for the devices. Yeah.
In several places I've read, there seems to be an online tool where you can take your iOS XE config, put it in there, and it'll tell you what's not supported. After you remove that, then it can generate templates for you. But I've not been able to find that tool.
So that configuration tool, if you put your XE SD-WAN, XE configuration in the device template, there will be a preview screen where you will have the differences from the vEdge and the Cisco devices. So with that, however, whatever the configs which we're going to put from the vManage to the device, it will be from the vEdge perspective, from the Viptela perspective. The XE configuration will be converted to the Viptela perspective and then go to the device. So if you put that, there will be a configuration difference, and it will say you that which one should be removed, which one should be needed, which is not there. So if that is not correct, the device template or the feature template will not get pushed to the device itself. I can put you on the WebEx team for that screen, actually. I don't have it here, but I can do that. It will give you the basic preview of the vEdge and the Cisco device, and you will be seeing what is there in the vEdge and what is not there and what is needed. That's what you needed, right? There is a config comparison tool as well. So whatever the configs which you do it in the Cisco device, you can convert it for the vEdge again. There is a configuration tool. I can send you that link as well. Yeah. And few of the platform serviceabilities. So
When were you going to send that?
I'll put it in the WebEx Teams after the session. Yeah. So there are possible control connection failures for the serviceabilities to begin with. So this control connection is for the controllers and the data plane devices for the routers. So what are the possible failure we would see in frequently, like connectivity issues or any certificate issues or serial number issues. So for the connectivity, it will be the DTLS connection failure, basically the link between the controllers and the data plane, which will be as DTLS or TLS connection. So that is broke down, or if there is any T-lock, transport location disables, or some transient conditions. And for the DTLS connection failure, so what are the probable causes? The basic things like next hop not reachable, or the default gateway is not pingable, it's not reachable again, it's not installed in the fib, or DTLS port is not open for some time. And here the debugging steps as we go, as you usually follow, which is again the ping the default gateway, see the reachability, ping the vBond IP address if the ICMP is allowed in it, and then trace route to vBond and see where it's dropping. So if there is a DTLS failure, if there is a connection fail, you will be seeing this dconf fail message in the show control connection history on your device. So if it's a dconf fail, it's the connectivity issue. You just have to go approach the process through the connectivity issues. There are a few of the transient conditions where system IP changed or teared down message from the vBond. So the error which you see here is this one, the disconnect vBond after register reply, or if there is any system IP change and it's not been updated on the controllers. And then there is the serial numbers. This is again, this serial number issues comes in place when basically the serial number which we upload, it's what we do. So either we manually do it or just download the file and then put in the controllers. So if there is any issues with the serial numbers, so on the edge devices, you would see as challenge response rejected by the peer. On the controllers, like the vBond, you would see as the peer board ID certificate verified. So both are referring to the serial number issues. And then for the certificate installation, if the root certificate is not getting verified from the vEdge devices or in the any of the devices from the controllers, if it's different, if the root certificate is not same as the controllers, then we would be seeing this certificate verification fail. And there is this organization mismatch. This again, basically for the controllers, for your devices, for your overlay network on the devices, the organization name should be same across your network, else there will be a mismatch and there will be a control connection failure again. So the possibilities like organization name may not get updated if you have changed it. So we should make sure that the controllers and the devices are in the same organization name. And then the dashboard. This vManage dashboard from my lab, which is again 19.1 release, the latest one. So here, if you see here, we have the vManage, vSmart, and the vBond are up and running. So that means the controllers is up. So and then the WAN edge is like 4 devices, wherein those are the devices got added to the controllers. So if you see there, one is down, like 3 are up, like 3 are up. So there are this control up, partial, and control down. So which means the total number of devices are completely controllable from the vManage itself. So you can do anything from the vManage for that device, like system statuses or upgrades or reloads or monitoring that device, interface utilization, like basically everything. And then partial up is device are in control for that, but not for all complete features. So there will be few other restrictions for that control connections. Control down is there is no access for that device from the vManage. So when I say no access, it doesn't mean that the device is offline or if the device doesn't pass the traffic. It's just that the control connection is down for that device. Your data traffic will not get affected. And there is a system status example. I've just taken 1100 series. So show system status on your device, you can do that. You will get the same information. Again, so basically what I'm trying to say is even the show commands can be viewed from the vManage dashboard. So if you see there the reboot information and the modules, the temperature sensors, the CPU, memory information of the device. So you can also see the real time and hourly basis, 24 hours. So you can also customize it. How do you want to take this out for the vManage dashboard with the memory and CPU informations. And then if there are crashes, all of this information from the vManage. And then this software upgrade. So there will be a software repository in the vManage dashboard. So you can just upload your iOS XE SD-WAN images in that. And then you can just come here, device list. You can just select whatever the device you wanted to. It can be of one device or multiple devices together. So if we just click on that upgrade option, it will pop up for which version you want to do it. If you have multiple versions for one device, it will ask for which version you want to choose for. And then you can just have to click on the upgrade. There will be a pop-up window for activate and reboot that image. So if you see in this vManage dashboard, I have available version of 2 of the versions. So I have loaded 2 of the versions, but then default will be 1. So one of the latest one which should be running. 16.9.4 is not latest, but that is the latest one I uploaded. So in this, you can choose to activate that image later also. So that's what I'm trying to say. You can load the image into the system, but not activate it. So if you activate it, the default version will come back, and you can choose between the versions. There's this reboot option again from the vManage. Any device or multiple devices can be chosen. And then there's alarm types. So if there are any issues in a network, you will get to know from the vManage. So any critical issues in the WAN network, you will be able to isolate where the issue itself is. So for the alarms, you'll have red or yellow, like major, critical, minor alarms. So if it's major or critical alarms, one of the hardware components got failed, the router has gone bad, or due to the temperature failure, router has exceeded its threshold limits, something like that, or critical, wherein the router is down basically. And for the minor alarms, like there's just like a warning. If you just leave it unattended, it may result in the router failure. And then this is the sample I've taken from the vManage. For the critical, if you see the BFD is down or the OMP is down, basically the control is down for that image, for that router. And then there is this minor alarm. Major alarms are control T-locks down. Minor is something like commit status, the config commit status. So these are the examples you can go through. And then the show tech, like admin tech from the vManage again. If at all you're going to open a tag case, so to get it to any of the Cisco engineer to review any of things, issues in your network or any of the logs or anything, you can collect this admin tech from the vManage itself, where it has all the vdebug logs, vsys logs, system statuses, if there are crashes like core files, crash infos, vdaemon logs, basically everything in the admin tech. Then the packet capture. So from the vEdge, for the vEdge, from the vManage, you can do the packet capture. It's for the XE SD-WAN is still not in support, but for the vEdge, you can do it from the vManage itself, wherein you'll be able to download the file as a PCAP file and then get it from this. You'll have to select the interfaces like service VPN or the transport VPN, and there are options. If you just see on the vManage dashboard, you'll be able to look into it. Again, there is also option for this from the CLI, simple syntax with TCP dump with VPN, where you'll be seeing the source destination IPs, UDP or TCP packet, and the port of it, the packet length of it, that's it. Then the packet tracer, this is our traditional packet tracer as we always use in our XE devices. So this packet tracer comes in place when there is a packet drop again, obviously, or if there is any lack of packets or anything at all in the data traffic. And this visualizes the FIA, the feature invocation array, and gives you the details of it. So for the debug platform condition, basically the syntax for the packet tracer, which is debug platform condition, the interface which you want to do it, and then ingress or egress directions, and then start that condition which you are given, and then enable the packet trace, test it, send the traffic. So show platform packet trace statistics. So in that, you can choose the packet you wanted to look over, the details of it. So I've just taken show platform packet trace packet number 8, wherein the state it gives you, the drop 20, and the source and the destination port. And it also gives you the feature, what is the feature doing it, the NAT, the old and new address of the NAT again, and little more details with the FIA, wherein it gives you the feature like FIA trace and the entry and lapse times for that, basically the complete details of it. And we are almost to the end. Thank you.
All right, guys. Before we conclude the session, anybody here is from St. Louis, from state of Missouri? Congratulations! First Stanley Cup, 52 years. Awesome. Unbelievable achievement. Unbelievable. Well, today we look at the platform overview. Then we go a little bit deeper. We open up the hood. We see what's under the box. We see the different part, the component, and how do we tie them together with the packet flows and with the software together with the FIA. And the key takeaway I hope you can bring back home is that you see that Cisco has the most comprehensive portfolio to support your SD-WAN deployment. If you just want to have a fabric connecting all the sites together, you can do that with a vEdge. Right? We call that the thin edge. If you want to have a rich services for your branch, you want to add in voice services, UC. You want to add the DIA, the direct internet access with a security stack, which we haven't touched, but there are many other Cisco slide sessions touching that part. You have the firewall, IPS, URL filtering, so on and so forth. You want to compute. We have the UCSE, we have the ENCS, has a compute capability. The ENCS can host the virtual network functions. So you have the industry-leading branch router, the ISR 4000, ASR 1000. Now, the ISR 1000 are part of the SD-WAN fabric. And if you want to connect in your data center, your HQ, with large amount of scale and the performance, you can do that with Cisco ASR 1000. And everything we put together in a simple way because there's a single UI to support that SD-WAN fabric. And if you have the Cisco ISR product already, ASR product, you can migrate them easily just by loading up the SD-WAN image. We didn't talk about the simple steps to complete the migrations. And we're adding a lot of functionality into the vManage to make it more available for you to improve the serviceability of the SD-WAN fabric as well as the individual device management. So the call action is, if you have not started the journey of the SD-WAN, you only started learning, well, go to the next go to the next step, right? Start the POC. Start your lab. There's a Cisco dcloud. You can go to the dcloud.cisco.com. Go to the SD-WAN lab. Try it out. Well, if you already started the POC, is working for you, then go ahead and start deployment. And the Vijay, he's the, did you hear his job title? What did he do? He's the escalation engineer. So when you get into troubles, send him emails. He's the one going to save your day at the end. Well, guys, thank you very much for coming. I really appreciate you coming to the 8 o'clock session right after the Cisco Appreciation Night. And I hope you guys have a great day. And this is the last day for Cisco Live, and you have a safe journey back home. Please make sure complete the survey and put all the goodies in the score. Put the feedback just as comments, okay? Thank you. Thank you very much.
Guys.